Chapter 7, we're going to look at complex numbers. And complex numbers result from square rooting negative numbers. So for instance, x squared minus 4, we'd subtract 4 from both sides. And we would normally say, well, we can't square root this, there's no real solution. But there is a complex one. The square root of negative 1 we call I. And it follows then that I squared is equal to negative 1. Now what we're really doing is we're splitting this as such, and the square root of negative 1, we just said that that's I. Square root of regular 4 is 2. So we can say that the solutions to this quadratic are plus and minus 2I. The second one, well, we can't factor it, and I wouldn't use completing the square personally. I would probably use the quadratic formula. So I get 1 plus or minus the square root of negative 7 over 2. Well, square root of negative 7, that is going to be I times the square root of positive 7. A lot of times you'll see complex numbers written as the real part, 1/2, then plus, minus, I times the square root of 7 over 2. Or you might have just left it as 1 plus or minus I squared of 7 all over 2. Either way is fine. A lot of times complex numbers are written in the form A plus BI. You're going to see this kind of notation in a lot of problems that you do. Now, because of this idea of complex numbers, we can factor anything really. Because for x squared plus 4, we know that zeros are plus and minus 2I. Well, when we factor stuff, we set the factors equal to 0. We then solve for the variable. Here we know zeros, we can write factors. X minus 2I and x plus 2I. X minus the two zero values. We can even factor k squared plus 11. The zeros are plus and minus I squared of 11. There's the factored form. So here we're solving a cubic. Well, we can try to factor. We know that x equals 0 or x squared plus 2 equals 0. X squared plus 2, not immediately factorable. We can subtract 2 from both sides. And we find the other two zeros are plus and minus I times the square root of 2. So this graph, if we think about it visually, only has one x-intercept at x equals 0. The other two are imaginary numbers. Here we have two complex numbers, z and w. We want to find their sum, their difference, their product, and their quotient. So for z plus w and z minus w, it's just a matter of combining like terms. 7 plus I, 3 plus 4 is 7, 2i plus negative I is plus I, z minus w. Now you got to be a little careful with the subtraction because you have to remember to subtract both the 4 and the negative I. 3 minus 4 is negative 1. 2i minus negative I is 3i. Z times w it's just a matter of FOILing. 12 minus 3i plus 8i minus 2i squared. Now we have 5i total. And remember, I squared, that's the same thing as negative 1. So this last term, the minus 2i squared, that's really the same thing as plus 2. So our real part of this product is 14. Z divided by W to divide complex numbers, what we do is we're going to multiply both the numerator and the denominator by the complex conjugate of what's down here. So we have 4 plus I, its complex conjugate, we have 4 minus I, its complex conjugate is going to be 4 plus I. We're going to do that to the top and the bottom. And what you might notice on the bottom is that's the factorization for a difference of squares. We get 16 minus I squared. In the numerator, we have 12 plus 11I plus 2I squared. And now we just finished cleaning things up. 12 plus 2I squared, that's, remember, plus 2I squared, that's going to be the same thing as minus 2. So I have 10 plus 11I as the numerator. The denominator is going to be 16 minus negative 1, or 17. And written in the form a plus bi, we have 10 over 17 plus 11 over 17 I. So this idea of a conjugate, notation you'll see in the textbook is z with an asterisk. So if we have a plus bi, its conjugate is just going to be a minus bi. The imaginary portion of that complex number is just going to change signs with its conjugate. And one nice thing about conjugates that you should know is when you're solving for roots of a polynomial, we'll always get conjugate pairs. So if one root is negative 2 minus 5i, the other root is going to be negative 2 plus 5i. And knowing that those are zeros, we can write factors, x minus each of them. And because this says we want all quadratic equations, we're going to be multiplying by some number a, where a is an element of the real numbers. Now we just have to expand this nasty thing out. So we're going to have x squared plus 2x plus 5ix plus 2x again minus 5ix plus 29 is what we end up with as the constant term. And what I did was I combined those two products. Negative 2 and negative 2 is 4, minus 25i squared, so that's a total of 29 as the constant. Notice that the imaginary portions go away. So our quadratics that have those zeros are going to have the form a times x squared plus 4x plus 29, where a is any real number constant. And here are some properties of conjugates. If we have the conjugate of a conjugate, we just get back to where we started. If we have the sum or difference of two conjugates, of two complex numbers, and we take the conjugate, that's the same as adding the two conjugates. And the product and quotient of two terms and then taking the conjugate is the same as taking the conjugate first and then multiplying.